Okay. We proved the frozen in approximation. Um, there's one more way to think about this adiabatic invariance. An adiabatic invariant is P dot ds around the closed loop, right? Now P is equal to mv minus e a over c, right? Okay. Closed loop of e over c a dot dl is equal to the integral of b dot d I'll use for area I'll use small a because b is the curl of a e over c. No. ds equal e over c b dot d. Now this closed loop, of course, is the gyro radius of the particle. So if P is proportional to 1 over S, and by the way, mv dot the if v is proportional to 1 over integral ds, v is a constant and it's parallel to ds because we're integrating around the path of the particle. And then suppose I lower b. No, I'm sorry. I want b squared to be proportional to 1 over. So we'll say it's proportional to 1 over rg. Well, in fact, I'll put 2 pi here to remind you that it's the full ds. If v squared is proportional to no, I'm making this up as I go along. Let's say v is proportional to 1 over rg. So suppose I change b very slowly. What happens to the particle? Well, v is going as 1 over b. No, I'm not sure I want to say this. No. 1 over 2 pi MVC over EB. So V squared is proportional to EB over MC. Now, what can we say here? For an adiabatic process, there's several ways to intuit this. First of all, this is the gyro frequency, cyclotron frequency. Cyclotron frequency. Means the kinetic energy of the particle, if B goes down, V squared goes down in proportion. So the integral of ds, which is equal to 2 pi rg, is proportional to b to the minus 1/2, right? And the flux of b dot dA is equal to a constant. That's how things transform under adiabatic process. So mv squared times the area is an adiabatic invariant, and the flux of B through the gyro radius is an adiabatic invariant, and you can see that omega, this energy is just proportional to omega, because quantum mechanically the frequency of a state is just the energy, and it happens to be the same as mv squared. And in Landau levels in solid state, the energy of the Landau level is just the kinetic energy of the particle that's gyrating. It's sort of gyrating because of 0-point motion, so it's not really a circle. The wave function is not particularly circular, but classically, the classical analog is that it's gyrating. Excited Landau levels involve kinetic energy. The lowest level may be zero kinetic energy, but the excited levels in solid state, it's just the particles gyrating around. As you intensify the field, you have more, the gyro radii decrease, which means you have more Landau levels per unit volume. So given energy surface, if you intensify the field, the energy of the Landau level goes up, because V squared, for that same state transforming adiabatically, V squared is going up in proportion to B. But as we said, the the magnetic flux is trapped in the plasma, but it's because it's trapped within each particle gyro radius. Particle is always gyrating about the same number of magnetic field lines in MHD. And that's another way of looking at frozen field. Okay, now this was all part of, whoops. Okay. Now let's go back to the MHD equation. Ideal MHD. dBdt is equal to curl of U cross B. Now, it's very easy to solve this. Just make U parallel to B and dBdt is 0. Because the right-hand side is exactly equal to 0. But suppose we also want to solve not just the MHD equation, which is the kinematics of the field lines, that are passively following the velocity pattern. But what if the field is exerting force on the particle, on the velocity, and what if B actually affects U? Well, suppose we say that U is parallel to B, and its magnitude is 4 pi B over square root of 4 pi rho. Then, and also we take the pressure to be minus B squared over 8 pi plus constant. This is the gas pressure. So the gas pressure is exactly filling in what this is called. The B squared over 8 pi is the magnetic pressure, as we'll see in a minute.
What is minus?
It just means that the higher B squared over 8 pi, the less the gas pressure. So that the total pressure, B squared over 8 pi plus PG, is equal to this constant. Now, this is called the equipartition solution. It does satisfy Newton's law because the kinetic energy, it's called the equipartition solution because the kinetic energy, rho 1/2 rho U squared, equals the magnetic energy B squared over 8 pi everywhere, right? Rho U, 1/2 rho U squared equals B squared over 8 pi. And let's check that it does. This should be dot U. By the way, did you get, Rahul, the latest?
I checked my lab, I don't have it. I have to check some other folder.
Okay.
I will do that. It used to be on older laptop.
On the old laptop.
That
Okay.
died.
Can you log on to it?
Barely.
Well, please transfer all your stuff to.
I have some backup.
Check the backup. Okay. All right. This is Newton's second law. Rho times Lagrangian derivative of U dt is equal to the gradient of pressure plus the magnetic force. And let's plug this solution in. Well, the gradient of this term obviously equals a constant, right? The gradient of a constant, because PG was a constant minus B squared over 8 pi. So this is going to vanish, and since we're assuming steady state, this will vanish. and therefore we're left with this term and this term. And since we picked u to be proportional to b, modulo this square root of 4 pi rho, then obviously u dot grad u is equal to b dot grad b over 4 pi rho. So this is clearly a solution of this equation. And because this is equal to this, because u is equal to b, the divergence of u has to equal the divergence of b. If rho is constant, if rho is not constant, the point is, if rho is constant, then I can assume this is 0 in the solution, because div u is proportional to div b, because u is proportional to b if rho is constant.
But this is always right if rho is constant.
What?
I didn't understand what you said. I mean...
Oh yeah, you're right. If rho is constant, then
It's always right.
then it's always the case that this is equal to 0. Now, now what have I described? I've described an alphane wave in the frame of the wave. In the frame of the wave, everything is constant, and everything is satisfied. MHD is satisfied, Newton's second law is satisfied, and everything is constant. So this describes an alphane wave in the frame of the wave. And usually when you see alphane waves described, it's in the frame of the observer, and it's more complicated. Now, if the fluid is incompressible, P can be whatever it wants to be, and rho can be constant. So we don't have to. So we can pick this solution and not have to worry that PG wasn't proportional to rho to some power. See, what we have not solved here is the equation of state. If I put the equation of state in, P proportional to rho to the gamma, we didn't solve that. But if the fluid is incompressible, then P is not proportional to rho to the gamma, because rho is constant and P can be whatever it wants. So if the fluid is incompressible, we don't have a problem with the equation of state. If the fluid is compressible, then we don't really know that this is an exact solution, because we didn't necessarily satisfy this. In fact, we didn't, because there's no there's no general reason why there's just no reason why all three equations should be solved by this, because if rho changes, there's no guarantee that P changed. There's no guarantee that rho will change in such a way that let me put it this way. If you're following one fluid element moving along the field lines, B is going to change, and in general, P will change, and rho will change. But there's no guarantee that rho is going to change, that rho is going to coordinate its change with B in such a way that PG will be able to satisfy two of these simultaneously. So if the fluid's compressible, this is not generally a good solution. But for an alpha wave to first order, note that B, let's call this the z direction, BZ is equal to a constant, and rho UZ is also equal to a constant. So in an alpha wave, the forward motion does not change. The only reason it's a wave is because the only change in velocity is perpendicular to the 0th order magnetic field. And so here, you know what, I enjoy this well. So what is the field doing? Well, the 0th order field continues straight, and the reason the field with the same intensity, and the reason that the field wiggled is because I added a component perpendicular to the 0th order field, which means that the wave motion is just the fluid moving up and down. In proportion to the field. Now, when the field is pointing up, it's because the added field is non-zero. When the field is still pointing, oh great! Look at that! It just disappeared. When the field is still pointing in its original direction, look at that! It keeps disappearing. All right, I have all day. All right, so where's the field pointing in its original direction? Here and here and here. That's where the perturbed field goes to 0. I'll have to move the perturbed field was non-zero when it was pointing up, but here, when it's tangent, the perturbed field is zero, and therefore the wave velocity happens to be zero here, because it's reached the maximum and now it's going down. Now, the gas pressure obviously has to change. But it changes only to second order, because b squared is b0 squared plus b1 squared. So the gas pressure only changes to second order in the magnetic field. And therefore the density changes only to second order in the magnetic field.
Why is it? I'm sorry.
Why is what?
Why is it B0 squared plus B1 squared?
Because B is equal to B0.
So you have another term.
No. But the third term is 2B0 dot B1, and because B1 is perpendicular to B0, the cross term vanishes. If it didn't vanish, it would be changing the gas pressure would be proportional to the first power of B. And for a magnetosonic wave, that's when B1 is parallel to B0. Then the change in gas pressure is first order in B, and that's why it's called a magnetosonic wave, because it's combined the magnetic pressure change and gas pressure change. And by the way, for magnetosonic wave, this is no longer true. I mean, the pressure is no longer constant. It's just a whole different kind of wave. But for an alphane wave, to lowest order, there's no change in the density. And the pressure gradient is not really, the total pressure gradient is not playing a role, because the total pressure gradient, as I wrote here, is cancels out. For magnetosonic wave, the pressure is playing a role. That's what's moving it. In an alphane wave, it's this term that's
compressible.
That's exerting the force on the fluid. It's due to the fact that you're stretching the magnetic field lines, and they have tension, and they want to straighten out. So this is like sort of the magnetic tension balances the centrifugal force. Every time the fluid takes a curve, the centrifugal force pushing out is equal to the magnetic tension pulling it back in. So it's sort of like somebody, like a wrestler or a boxer bouncing off the ropes. When they stretch the ropes, except that instead of bouncing off it, a linearly polarized alphane wave when they keep bouncing off it back and forth, but in the frame of the wave, he's just moving. He's just moving around the ropes and following it. It's sort of like I don't know. He's just rolling along it, and they're stretched out, and he's rolling around the curve. Now, what if the fluid is compressible? I guess I just don't have a general answer here. If the fluid is compressible, in general, a large amplitude alpha wave, as I said, to second order in B, there's no change in density for an alpha wave, so it does not couple to acoustic waves, but in higher order nonlinear processes, an alpha wave can decay into a sound wave plus another alpha wave. In other words, the motion of the change in pressure causes a change in density, and that means that the velocity is no longer satisfied. It's no longer parallel to B, because rho is changing as you move along the field line, and you can't just say that this term is equal to this term, because you would have to, there would be derivatives of rho in there somewhere. Okay, now, what time is it? Oh yeah, we have to.
You're missing a gradient pressure.
Can't you rescale?
Right. What?
Take rho into x. I mean, you only have rho in the denominator with the gradient. So you rescale such a way that the new density is constant.
Well, here's the thing. If you want u dot grad u to be equal to b dot grad b of 4 pi rho, let's put the rho up here. Now I know that this is equal to 0, and this is equal to u grad rho plus and I also know that grad b is equal to 0, divergence b equal to 0. Alright, why don't we assign this for homework? What goes wrong? Let's put it up here. For homework, if rho can vary, why is this not an exact solution? And by exact solution, I mean that you have to satisfy this as well. I think that if the Maxwell's demons were there removing heat in such a way that the pressure always cooperated, you could arrange a solution with variable density, but that's not the way it works. You have no Maxwell's demons helping you out. All right, let's go to instabilities. The oh my no. Okay, this should be Tij. Uh, this should be amazing. This should be over here in the XY position, and here it should be XZ. The point is, this is just proportional to the identity matrix. What?
There's also the same term in the.
Oh, look, now I moved the I and the J. How do we do this? Alright, the point is that Tij is just Bi B times Bj, but there's also this diagonal term proportional to the identity matrix, and it's proportional to the sum of them. This is the stress energy tensor for the electromagnetic field, and you can if you take the divergence of the stress energy tensor, you get a force. Because force is the divergence of momentum flux, and stress energy tensor is magnetic flux. And this term here this term here is the divergence of energy flux. No, is that right? I'm not sure how to explain this term offhand. But the point is, if you take the divergence of Tij, which is dTij dx sub j. I think I called it, I don't know why I called it m sub ij here. It should give you a force, and it should equal J cross B plus rho times E, which is curl B cross B. J is what? C over 4 pi, right? J is the curl of B times C over 4 pi. And rho is the divergence of E times E. Sorry, there should be a C here, so there's no C over here. No C here. And rho is the divergence of E divided by 4 pi. Now, this term here divergence of E times E, dB dt, when I take the time derivative of B, I'm going to get E cross dB dt among other things, but this is E cross curl of E. And this is basically B cross curl of B. But remember, this means that I write the same matrix with E replacing B. So, what's Maxwell's equations? E of c dt is equal to curl B minus 4 pi J over curl B 4 pi J over C, yeah. Right? This is one of Maxwell's equations. Anyway, if you play around with this, Nicola assigned this for homework too. Just show that DIT IJ gives Lorentz force. It's in Jackson. Might as well do. In cylindrical coordinates, TZ's B phi squared minus BZ squared, and that's the momentum flux along a field line that has axis symmetry. This is shear force. Off diagonal terms in T are shear force, but this is momentum flow along Z, and you can see that B phi acts as a pressure. In other words, field lines perpendicular to themselves act as a pressure, but parallel to themselves. Like if I just had rings of B phi and BZ is 0, then it's a stack of pancakes, and it's like a slinky. It wants to compressed spring. It wants to de-expand because the pressure is positive. But when pressure is negative, it means that things want to shrink. And so here BZ is not 0, but B phi is equal to 0. Here they act like taut strings. They pull in. It's like a rubber band. And I don't know if I have a rubber band, but rubber bands behave exactly like magnetic field lines, because electric field and magnetic field, from the point of view of the stress energy tensor, electric field and magnetic field play exactly the same role. And in the rubber band, it's the electric fields between the atoms that play the role, but they're doing the same thing that magnetic field lines do in astrophysics. And if you stretch the rubber band taut, then it's under tension and it wants to pull back. But if you twist it so that you have toroidal fields, then it's under pressure and it wants to shoot out sideways. Shouldn't I have a picture here? Go back. instabilities. Ah, she didn't draw it in. Okay. She didn't know how to write a tech file. So the point is, if the field lines are like this, the stress energy tensor is positive, which means this is under pressure. It would like to increase its length. And if you hold this end fixed and this end fixed, what does it do? It can increase its length by doing this. So it expands sideways, and it's unstable. Whereas this, if you pluck it, it's under tension. The B dot. It's easier to see that B dot grad B in a situation like this is pulling back. So it restores it. So this is stable, and this is unstable, and this is called the kink instability.
Restores it?
In this case, it restores it.
Just does like this?
It's like a rubber band. Stretch a rubber band and then pull it sideways. It goes back.
It just doesn't go back. It does oscillations. Does it do that?
Yeah. That's an Alfvén wave.
Okay.
But I only drew the first half a cycle. Okay. Electric fields are the same. They're under tension along their length, and they're under pressure perpendicular to their length. And the inflationary universe, where the whole universe is under tension, the cosmological constant just says that there's a T mu nu term is equal to minus lambda, where lambda is a positive number, and it's equal to Tyy and Tzz. It's an isotropic tension. It's like a three-dimensional membrane that just wants to shrink. And in gravitation, that provides a cosmological constant. And everybody says, okay, what's the origin of this? Well, one way to do it is to invent extra dimensions and have the field lines at each point in our universe. There's a fourth dimension, say, where the field line is pointing in the fourth dimension. But that wouldn't do it. That would mean in our three dimensions it acts as a pressure. I'm sorry, I forgot. There's a way to get a negative pressure in our three dimensions from field lines that are in a fourth dimension, or maybe it's a compact dimension. No, but I can't think of how to do it offhand, because if you added a fourth dimension, you added a fourth dimension here, it would act as a positive pressure, just like these three. You would have to say that you have to say that T44 is equal to minus B44 squared plus BX squared YZ. But I'm not sure how to get the no, I don't see it offhand. I thought I did, but I don't. But the idea is to invent higher dimensions and put magnetic flux tubes in the higher dimensions so that in our three-dimensional universe you can play games with this energy momentum tensor and have extra terms in you could have dark energy for no particular reason, even though it's not associated with anything in our universe, just by having flux in extra dimensions. Okay, well I see I went way past time, so.
If you have flux in extra dimension in, let's say, in our universe, like a surface in that extra dimension, so you
Yeah.
need a particular field at every point.
Yeah, but that should be a pressure, not a tension.
That would be a scalar.
It would be a scalar pressure, but it would be positive. It would be a positive. It would give you anti-de Sitter space instead of de Sitter space.